Hey there guys, just wanted to give you a little help with number 11 talking about golden rectangles. This idea of phi, or the golden ratio, sometimes it's pronounced phi also, is one of the coolest things I've run across in mathematics. It's found in nature, sequences, it's kind of hidden in a lot of different places, but we're going to talk about it with rectangles. And just to give you a little help with A, we have to find what the actual exact and approximate values of phi are. Now they have the ratio set up for us. Phi is the ratio between this height and this width, essentially, for this rectangle. So even just calculating it, sometimes instead of seeing it as phi, sometimes if we just write it as x is usually all I need to help students with. In fact, just seeing that we can multiply by x to both sides if we're going to solve for x. I get x squared equals x plus 1. From there, you can notice that it's a quadratic, and you might have to do a little algebra from there, but you can actually find an exact and approximate value of that. So pretty straightforward on that. Now B asks to determine the which are golden rectangles in this case. You actually have to measure it. So you may have to find a ruler. That's why you gave the worksheet to give you those ratios. And then C is a rectangle ABCD similar to rectangle PQRS. Again, match up the side lengths and see if that ratio is actually there, whatever that decimal is. If it's close, it's probably a golden rectangle. But then they ask, is one similar to the other? What I want to help you with actually is more with part D. Prove or disprove that all golden rectangles are similar. Now, I don't know if these two are. I'm pretty sure they're not. But let's say ABCD is golden and EFH or EFGH is golden also. I want to show you what you would have to show to see if these are actually similar. With any similarity, what we want to show is matching corresponding sides. Like I would want to match AD to EH. But I don't know anything about AD and EH. All I know is these individual rectangles are golden, or they have the golden ratio with them. So what I can do is actually start talking about each rectangle individually. Like if I take AD divided by AB, what that might equal. Well, we know from up here, if I take that length divided by that length, that equals phi. Now, separately, if I go over this triangle, I can actually say the same thing. Now, I don't have a relationship linking the two triangles or the triangle sides yet, but individually, we could say EH divided by EF is also phi. It's just that ratio between those two sides. Now, we've seen a lot of this in the last coming units and things like that. If I have one thing congruent to the same thing or equal to the same thing, I can do something with those expressions like AD over AB equals EH over EF. The reason being that's a substitution. Now from there, I'm going to leave you to see if you can rearrange this to think about, well, I got to get a link from like AB to EF. That ratio, if these are going to be similar, is going to be the same ratio as AD over EH. So if I get that ratio, AB over EF and AD over EH, then I know these two are similar because when it's a rectangle, I can say the rest of these sides are going to have that same ratio because they're all congruent. This one's congruent to that one, and this one's congruent to that one. So the ratios continue on to those other sides. So see if you can follow that logic, have some explanations of what you're doing to see if you can link that relationship with this side over to this side and this side over to this side to see if that is that same common scale factor of k. As mentioned, just as a last note, a quick Google of phi, you'd be amazed at some of the places you can run into this ratio, not only in rectangles, but in spirals. Like I said, Fibonacci sequence is a pretty common one too. So have fun with it, maybe investigate a little more, and I'll see you in class.